welcome back. This is the first of three lectures on forces dealing with Chapter 5. Now, um, this particular lecture isn't done in a consistent order with your book because I feel that it's better to be presented with Isaac Newton's three laws before you actually start doing examples so you can pull from all three of them. Now, that said, if we're going to talk about forces, we do need to talk about Isaac Newton. Now, as you can see, he was born in 1643 and he died in 1727. Now, roughly around 1660 or so, he was encouraged to attend college, specifically Trinity College in Cambridge. Now, college back then for a student was a little bit different than it is today. Back then, unless you were able to get a scholarship, pretty much any finances the college required came out of your pocket. Now, Newton was lucky because he was able to obtain a job on campus to help pay for his college. And then when he finally got to the position to where he could get a scholarship, he was set. Now, in 1665, Trinity College closed because of an outbreak of the Black Plague. Now, Newton had just graduated with his bachelor's degree, and he was focused on graduate work, primarily dealing with picking up the mantle of Galileo. Now, we're going to talk about that here in a moment. What I'd like to do, real quick, briefly at least, is to talk about the Black Plague. Now, this right here is a plague doctor. Now, most people, I'd imagine, have seen this. You see the bill like that, and maybe it invokes some, bad period PS4 movie or something like that. Back then, though, there was no germ theory of disease. So, the bill here was actually packed by doctors with garlic and strong smelling herbs because they believed that strong smells would ward off the plague. Now, this thing right here showed that they were in fact a doctor and also allowed them to poke people on the ground to see if they were dead or not. The plague was not a joke. Even by today's standards, it's bad. For example, we know it as the bubonic plague. There are actually three types. The bubonic is one. You have something called the septicemic plague. And then you have something called the pneumonic plague. GUE there. Now, they're all caused by the same bacteria, and that's what causes it is a bacteria. But even by today's standards, like I said, if you were to get the bubonic plague and you got antibiotics and modern treatment, there's still roughly about a 10% chance that you might die. The septicemic plague is much worse. If I remember correctly, you're looking at something like a 90% chance of dying with care. The pneumonic plague is 99%. It's 100% fatal if you do not get treatment within 24 hours of presenting symptoms. So, as you can see, the stuff isn't a joke. It's so not a joke that the first real big recorded Western outbreak was called the Justinian Plague. it ravaged Europe for centuries, and they're pretty sure it was responsible for killing about 50% of the population. So it's not that 50% were infected by it; it's that 50% were killed by it. So that said, uh, the people at Trinity College weren't stupid. They knew that they needed to shut down and get people out because the solution to dealing with things like that back in the day uh, was to quarantine. The idea is you quarantine, you don't let anybody out, and eventually the last person who can get it will get it, and either they'll die or they won't, and then you open things back up and the plague is gone. So in 1665, like I said, they closed the college down, and Newton actually came from a wealthy family that had a lot of property, and um, and he ended up sort of heading back home, and he lived on an apple farm until about 1667. So for about 2 years here, Isaac Newton is actually continuing his work, primarily dealing with this mathematical theory that he was developing called the calculus variations. He worked on theories of optics, theories dealing with just physics in general, like his mechanics that he was developing. And when he came back, roughly around 1667 to Trinity College, he was made a fellow of some sort, and continued his work. Now, the big thing that he published that he's really, really, really well known for was published in 1687. It was the accumulation of all of the work that he had done. Uh, it's typically just referred to as the Principia. But in English, it's called the Mathematical Principles of Natural Philosophy. Now, natural philosophy is also known as physics. And inside the Principia, you're exposed to Newton's calculus, his three laws of motion, and also a law of gravity. So it's a huge deal. This book was a game changer. And it's from the Principia and his three laws of motion and the law of gravity that you get things like the entirety of University Physics 1. That's what University Physics 1 does, is basically the material that's inside the Principia. Now, so that said, pretty much everything he touched with respect to the sciences, he made some pretty substantial contributions to, from especially his optics. He developed a type of telescope, for example, that uses mirrors instead of lenses. It's called a Newtonian, and it is the most common telescope that you see used today in astronomy. So he did quite a bit of stuff. Now, that said, what I'd like to do now is to talk about the three laws that were in the Principia, specifically because they form the foundation of classical physics, basically. Everything that you learn past today will draw from the three laws because Newton did a great job. He did a fantastic job. Uh, you know, the only thing that we really had to do was to change gravity a little bit and then amend, his theories to account for things that are very small and to account for things that are traveling very, very fast or have lots of mass. So the first law looks like this. A body at rest remains at rest, or, if in motion, remains in motion at a constant velocity unless acted upon by a net external force. Now, we're going to pick this law apart here in a moment. But before we do that, what I'd like to do is to introduce something called inertia as a concept. Now, inertia is an object's tendency to resist having its motion changed. resist changes in its motion. So, as an example, let's pretend that you had a car and you needed to push it, say, off the side of the road or something like that. Well, you know that getting the car started rolling takes a lot of work. And that's because the car has a bunch of inertia. So you push on it, you exert a force on it to change its motion. And as you do so, you fight its inertia. As you push it faster and faster and faster, it still fights you. But the minute you're able to get it rolling at a constant speed, it doesn't take a whole lot of effort to keep it going. Now, that is a simple example of Newton's first law. Objects like to remain at rest, or if they're moving, remain moving. This contradicts Aristotle's view of physics, if you remember way back when I said that the Greek view placed objects at rest as their natural state. Here, an object's natural state is to continue doing whatever it's doing. If it's at rest, it likes to stay at rest. If it is in motion, though, it likes to continue moving at a constant velocity. Now, that said, obviously things change in motion. They have their motion change all the time. So, what causes that change in motion are forces, specifically net external ones. So let's dissect this right here. The term net means to add up. Okay, so as an example, back in chapter 2, back in chapter 4, when you were dealing with vectors, you know that you can add multiple vectors together to get one overall vector like that. That is the addition of vectors to find the net vector. You add them up. External means outside of. So here, the forces that we're talking about that cause changes in motion come from outside of the object. Now, objects don't influence themselves is the key point here. And you might look at things like rockets and say, well, clearly they do. Well, it's more complicated than that. And in reality, they don't. And we're actually going to talk more about that when we talk about momentum and its conservation principles. So, an example of an external force might be you pushing on something with your hand, gravity, springs, anything that can push on something or pull on something is considered typically an external force. Now, so it's a force. Well, forces are things that cause changes in motion. I'm going to put here in parentheses, potentially, changes in motion. Now, the reason why I say potentially is that forces have magnitudes and they have directions. They're vectors. So you can imagine a situation where you have an object like a box or something like that, and you push on this side and on this side with exactly the same amount of force, but just in opposite directions. Well, if you remember vector addition, if you take a vector and you add the negative of the vector to it, you end up with the zero vector, or zero. So in this case, you have forces that have added up to cause no net external force, even though individually they're non-zero. So you would not expect something to experience a change in its motion at that time. On the other hand, if you took one of these forces away, like for example this, You just push on it from here. Or maybe you pushed on it with multiple forces, but ones that won't cancel each other out all the way. Then you will have this object experience some change in motion. Now, that said, one way of looking at Newton's first law is this. Anytime you see an object go in a straight line at a constant velocity, you know that the net external forces on that object have added up to be zero. But anytime you see an object who experiences a change in path like that, or even an object who's traveling in a straight line but goes faster and faster and faster, in that situation, you know that net external forces are present. So Newton's first law is sort of a diagnostic tool. It allows you to look at an object's motion and immediately determine as to whether there are net external forces present. Now, that said, we're going to come back to this here in a little bit, but I would like to also tell you about the other name that we give Newton's first law, and that is the law of inertia. Okay, so you can see how it relates to the definition of inertia. Now, so let's talk about Newton's second law. Now, Newton's second law here is a math law, okay? So the first law tells you the conditions under which objects experience changes in their motion. There have to be net external forces. The second law tells you how those forces actually relate to the change in motion. Now remember, acceleration is defined as, from an average standpoint, how an object's velocity changes over time, or from a differential standpoint, the derivative of an object's velocity with respect to time. In both cases, you're asking the question how something's velocity changes. That is, how its motion is changing. So if its motion is changing, that means that there's an acceleration present. If there's an acceleration present, it relates to the forces that are present in the following way. So let's talk about what's going on here. So the first thing I'd like to point out is that you have this sum here on the left-hand side. That is your net external force. So remember, net means to add up. So, for example, let's pretend that you had, once again, your block or something like that, and you push on it like this, and you push on it like this. You've got two forces present. So we'll call them F1, and we'll call them F2. Well, in this case, the net external force would be what you get when you add them up as vectors, F1 plus F2. And the way that you represent addition like this, or at least one of the ways that you can represent it to make your life easy, is through a sum. You're adding up all the vectors indexed from 1, in this case, to 2. Okay, so this gives you the net force. And it's all of these forces acting together that causes your object, which has a mass, this is your object, to experience an acceleration. So some people, if they haven't had physics, when they look at this equation, they say, okay, well, clearly, accelerations are the things that cause forces. That's not true. Forces cause accelerations. Okay, forces are the origin of changes in motion as laid out in Newton's first law. Okay. Now, inside this equation, we have a couple of important things other than just the relationship between the force and acceleration. The first thing I'd like to point out are the units. So this tells us what the units of force are. So mass here, we think of as the amount of matter in something. That's a chemistry definition. The amount of matter inside something. But perhaps a better way of thinking about mass is this. Mass is the thing that resists your change in motion. It's analogous to inertia. And you can see that by solving for acceleration here, which we're going to do shortly. So that said, in the metric system, we measure mass in kilograms as the base unit. Acceleration, we have a pretty good familiarity with. It's meters per second squared. So this set of units right here, this derived set of units, forms the base unit for force. We call it the Newton, and it's abbreviated as N. Okay. Now, that said, let's look at this again, and I'd like to solve for acceleration. And to do that, all you do is divide both sides by m. So the acceleration that something's going to experience due to all of the forces that are acting on it depends upon its mass, and it depends upon it in an inverse way. So as m gets big, that means that acceleration gets small. Okay? As m goes small, acceleration gets big. So, like I said, this is basically inertia. And the reason why we like to think of it as inertia as opposed to just strictly the amount of matter inside something is because as you get further and further into physics itself, you discover situations in which the amount of matter and the amount of inertia that you're looking at don't match up. For example, when you're doing relativity or looking at the properties of light. So, here's what we have so far. We have one law that tells us the conditions under which objects experience a change in motion. There has to be a net external force present. And like I said, it's like a diagnostics thing. If you see an object experiencing a change in motion, you know that there are net external forces present. Then you have a law that relates that change in motion to the forces that are causing it. Now, finally, we have Newton's third law. Now, Newton's third law, it's got a lot of words, right? Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. Mathematically, if the two objects are A and B, the force of A on B is equal to minus the force of B on A. So imagine having two objects here. I'll call it object A. I'll call this object B. This right here is the force that A exerts on B. Now, the act of pushing on this thing, exerting a force on it, we know, according to Newton's second law, causes an acceleration, right? Well, remember, this thing is fighting its inertia to get it to accelerate. So as a consequence, because it's fighting the inertia, there is a force back on A, okay, that's equal to the force that A is exerting on B. So that's what this says, is the forces are equal but opposite direction. Now, we're going to be talking more about this later on because it's an incredibly important law. We know this is the law of action and reaction. And in truth, the term action is what Newton referred to as force. Forces act on things. So, that said, let's think of one or two examples of where you might see Newton's third law in application, if you will. If you take, for example, and let's pretend that you got a cup of coffee. You put a cup of coffee, we'll say, on a countertop. So there's your cup of coffee right there. There's little coffee fumes coming off like that. Well, the coffee itself has got mass. Okay, quote unquote, it's made out of matter. And it's in the presence of gravity. And gravity likes to pull things down to the ground with an acceleration, right? So there's a mass that's present. There's an acceleration present due to the fact that you have gravity. Now, the presence of this desk doesn't somehow negate gravity. Gravity is trying to pull this cup through the desk down to the ground. But this desk is made out of matter as well. and that matter is held together very strongly via atomic and molecular bonds. So as this cup pushes into the desk exerts a force back on the cup, pushing back up like this. Now, in this case, these forces balance each other out. They balance each other out to produce a net force that's zero, which means that if the net force is zero, the net acceleration is zero, which means that the coffee cup is going to remain at rest on your desk. Okay. Now, this force right here that the desk gives back because it's being pushed on like this has a specific name. It's called a normal force. And we're going to do lots of examples dealing with it and some other common forces that we see in the next two videos that I do for this chapter. So here's what we have. We have three laws. A diagnostic law that tells you the conditions under which you see things experience a change in their motion. Then we have a law that tells you what causes that change in motion, forces. Then we have a law like this, which explains how objects interact with each other. Okay, so three very important laws that you can take and you can use the calculus with and derive the entirety of University Physics 1. So we're going to stop here in this lecture. I know it's a short lecture, but like I said, my goal with this one is to simply get you thinking in the direction of these three laws. We're going to be using these three laws from now on through the end of the semester and also through University Physics 2. They're that important. And I will see you in the next one.